In this study, we explored the mechanisms that ants use in order to locate their colony when foraging for food. It is found that ants utilize positive feedback via pheromone trails laid by foraging ants in order to share information about food sources, with visual memories for guidance acquired along routes. For many species of ants, a positive feedback mechanism in the form of pheromone trails, chemicals deposited by ants that have found a profitable food source, connect the nest with the food source. These trail systems provide a mechanism to reduce search or travel time by directly channeling foragers to a persistent resource. Where landmarks are altered, ants will naturally follow a compromised path between familiar landmarks and the pheromone trail. This influenced the approach of the study. By altering landmarks and interfering with the pheromone trail, it was hypothesized that we would observe a prolongation in the total time it would take for ants to locate the food and return to the nest. Previous studies have shown that ants will demonstrate a preference for the food sources containing carbohydrates, such as sucrose, rather than foods rich in proteins, such as freshly killed insects. This determined the food source that we would use in the experiment. There were 5 treatment groups used in the experiment. Treatment 0, which consisted of no landmarks. Treatment 1, which contained 1 landmark. Treatment 2, which had 2 landmarks. Treatment 3, which had 3 landmarks, and Treatment 4, which had 3 landmarks that were all rearranged. The experiment was conducted by placing 1 ant colony in an enclosed cardboard box. To ensure the ants didn't escape, the walls were covered with baby powder so they were unable to crawl up. The box was covered by paper that had holes poked through to allow the ants to breathe. 2 cotton pads, one containing honey and the other a sugar solution, were placed at the other end of the box, directly opposite the colony, so the ants would have a direct path to follow between their colony and the food source. Landmarks were collected from a garden: a leaf, a piece of wood, and some dry grass. These specific objects were chosen as they were found in an ant's natural habitat, so it would not impact the ant's behavior unnaturally. These were placed within the pathway between the colony and the food source to ensure the ants would interact with their landmarks. For each treatment, 6 ants were timed to move from the food source to the colony. Each treatment was replicated 3 times with a minimum of 24 hours between each treatment. Treatment 3 and 4 was performed in the same day to observe whether altering the landmark locations affected return time of ants. Comparisons between treatments and replicants were then made, and appropriate statistical analysis was performed to test for significance using PAST. Visual comparison of the average return time for each of the first replicants found treatment 0 to have a lower return time than treatments 1, 2, and 3. Visual behavioral indicators showed that the ants explored the newly placed landmark on the ants' journey back to the colony. However, statistical analysis with ANOVA using Tukey's test post hoc found no significant difference between treatment 0 and the rest of the treatments. We then compared the return time of the third replicates of each treatment to determine whether addition of landmarks assisted in an ant's speed in returning to the colony. Like the previous analysis of the first replicants, we were able to visually observe that the T0 had a higher average return time. However, statistical analysis did not show any significant difference. Comparing treatment 3, replicant 3, with treatment 4, replicant 1, which was performed right after, showed that the latter had a higher return time, possibly suggesting that the reassortment of landmarks may have confused the ants during their return to the colony. However, statistical analysis wasn't able to show significance. Replicates were performed consecutively from one another, and from this line graph we observed the average return time of replicates 2 and 3 were lower than replicate 1. Statistical analysis using ANOVA comparing replicate 1 and 3 showed that only treatment 2 had a significant difference. This difference is likely a result of pheromone trails which had been left from prior replicates. Our results reveal that both pheromone trails and learned visual information from landmarks interact and play an important role in guiding the ant species to a previously used food location. Previous studies have revealed that ants respond to an environmental change, such as the addition or change in a landmark, by strongly increasing pheromone deposition immediately after experiencing the change. However, while we were able to see a difference through observational behavior, analysis with ANOVA was unable to prove a significant result. A possible increase in replicates may have allowed to show significance. It is worth noting that we had no method for identifying individual ants. Numbered metal tags are often used for wildlife tagging, but that was not a possible option for this experiment. As a result, it may have impacted the observed behavior. That is, an individual ant that is already stressed from an early experiment may have been used again randomly, which could affect its behavior in the second treatment. Because the time intervals recorded for each ant to return decreased as more ants returned to the colony in all treatments, it appeared that the ants were able to find their colony more easily using the fresh pheromone trails left by the ants that recently returned from the food source. Social animals, especially eurosocial insects such as ants, have to contend with a constantly changing environment, which is why they rely heavily on communication, such as pheromone trails, for their success. In conclusion, the ants relied more on pheromone trails left by other ants and pheromone release from the queen ant than placement of the landmarks.